Alright, so I'm going to show you some integration with Coulombs law. So we have this infinite line of charge here. Okay, and I know that's not feasible in the real world, but if this if we were to imagine this being like a meter long and this being like a millimeter distance away or something, um, it would be almost infinite, and we could theoretically ignore edge effects at that point. And so this is what this is saying. We could ignore edge effects. It's theoretically infinite line of charge. Um, but let's get started. And so let's just draw some like lines here. And so we have some angle, right? And from to this point, and we have the dead on. And so I want you to realize that each of these little DQs. So so basically we have these little, let's call this uh distance. Let's set up our plane here. And so let's have uh this be our x and this be our y. Uh we're not really going to use y, but sure. So I want you to see that basically each of these GE um, basically these y values will end up canceling out here. Well, I'm just gonna stick with our normal system here. Let's do y and this is x. Alright, so each of these little charges here, these at these angles will cancel. Right, so the only thing we have to really consider is the electric field in the x direction. So dE x. And so we want to consider how each of these kind of um, DQs pushes the or contributes to the electric field in the x direction. And we can't just say, oh, let's consider this point, because each of these DQs is going to impact the electric field based upon their angle theta, which is why I'm drawing these. But it is important to realize that the y components here cancel out. And so the only thing we really have to consider is the x component. So let's start drawing our some triangles here. So we're going to call this, actually let's not call this theta, let's call this theta, because we want to find the relationship between this length A, this is length A from the rod to whatever point we're doing, and we're going to call this, I'm just going to call this, what should I call this? B. And we're going to call this R. So each of these has a little height here, and we're going to call that GB. That's definitely not good. D little b, because I am extremely creative. And so each of these also has a DQ. And so, and I'm also going to just say, hey, it has a lambda here, which is a charge per unit length. So we know that we're going to start DE here. The electric field is equal to kq1 over r squared. So the electric field, but we're doing this at a infinitesimally small level here for the tiny change in electric field and the tiny change in charge. So we're going to do dq over r squared. And so what we can do now is we need to try and find what this r is. And so we can rewrite this so we have k, and now we can say, and we also know that lambda dx is equal to dq, because the charge is just because lambda is defined as dq dx, right? We can just move this to the other side and say replace dq with lambda dx, which we have just lambda and we have dx, which is just a tiny change in something, this distance. So we now have to do r squared, and so we want to find the electric field from some point, and so we have a squared plus b squared, and actually we're going to call this x so that this will be dE in the x direction. So we're going to call this actually x. Yes, I'm changing my variables frequently, and I do not care. So we're going to just call this, by Pythagorean theorem, that this r is going to be a squared plus x squared, and we're going to square it so we don't have to have the square root. So x squared plus a squared. I don't even have to have an absolute value because they're squared anyway, which is pretty cool. So now we need to think about this angle here. And so let's look at specifically the x direction. dE in the x direction is just going to be dE times cosine theta. And so because cosine is adjacent over hypotenuse, this a over r, we're just looking at this horizontal x direction. Yes, I know x is both the y, or the horizontal and the vertical axis, and oh well. But we're going to say that we were looking at this, right? This dE in this direction. So we now need to find whatever this cosine theta is. We need to solve for a cosine theta. And like I just said, cosine is the adjacent side over the hypotenuse, which is a over r. And so we know r is this square root of a squared plus x squared. A squared plus x squared. And so now we can substitute this back in for dEx. So we have dE, which is this. So it's k lambda, so y, lambda dx times x squared plus a squared, and then we're going to multiply this by a over a squared plus x squared, and then we're just going to take the square root. And now this is all dE in the x direction. So I can write dEx. dE in the x direction. And so if we integrate this, we're going to get dE. So this is equal to, no, I'm sorry, not dE, just E in the x direction, which is what we're trying to solve for. And so we need to integrate this from some bounds of integration. And because this is an infinite line of charge, we do from negative infinity, I don't know what that was, to positive infinity. And so we're going to look at anything we can pull out of this integral here. So I'm just going to write, I'll do this. E in the x direction is going to be, well, lambda is a constant. K is a constant by just default. And if we're not changing the A value, we're just trying to find the electric field at a point, A is a constant too. And so we can pull all of those things out of the integral, leaving us with some things left. So let's see, I said we can pull out K, lambda, and I'm just switching my lambda back and forth, but whatever. A. And then we're going to integrate from negative infinity to infinity. And then we have left on the top this dx over. And so this is, we can kind of add these exponents when they're being multiplied. So if we consider this to be a 1/2, this would be x plus a to the 1 plus x plus a to the 1/2. And so we can just say the whole quantity down there is going to be x squared plus a squared all to the 3/2. So now we can start doing some integration here. And if we just substituted infinity like it was a limit and did some limit properties, we can we're just going to do some implied limits here. This is an improper integral, but it should be all good. So k lambda a. If you've taken a Cal 2 class, then this should be fairly obvious, and you would probably be in Cal 2 if you're taking electricity and magnetism anyway. So we're going to just substitute in things. So we're going to first substitute this into our, or actually we're just going to write up the proper integration. So when you integrate this, we're going to This is 1/2 on the bottom. So we're going to do... I'm trying to do this in my head. Let's see. X squared plus a squared to the 1/2. Because you add 1 to the denominator. And then you do the derivative of that. And oh, then we need this plus this a squared to be in there. And I think I have everything for that integration. And then I'm just going to write our bounds of infinity. So this is going to be from negative infinity to positive infinity. And now we can begin substituting. So, first of all, this a cancels with that a. And we can pull out the 1 over a. So we're going to do k lambda over a. And then so x at infinity over, so at infinity a is going to be theoretically or essentially 0. And so we're just going to write over infinity squared plus 0 to the 1/2. When you take limits at infinity, any other terms that aren't the highest power terms are basically inconsequential. So the a is essentially 0. And so we just have infinity squared to the 1/2, which taking the square of a square root is essentially 1, and if they're approaching infinity at the same rate, which they are, this becomes 1. So let's now do the minus infinity. So we're just going to subtract the negative infinity over negative infinity squared to the 1/2. And so this, like before, we're going to have to kind of think about this. This becomes positive infinity because it's just squared. And the square and the square root cancel. And so it's just going to be 1 minus a negative 1, which is 2. So the final electric field on this infinite line of charge is just 2k times the charge density over the distance from the rod. You would think it'd be like infinite, but it converges, which is pretty amazing. So that is infinite line of charge.